Hello and welcome. In this video, we are going to look a little further at differentiability for piecewise functions. In this warm-up, we're going to talk then about the derivative of sine and cosine, and we're going to wrap up with the relationship between position and velocity functions and tie that into rate graphs. So I encourage you to pause this video and work through the warm-up on your own, and then unpause the video and see how you did. So the very first thing that we should do anytime we see absolute value in calculus is really just rewrite it as a piecewise function. So this would be negative x, or the opposite of x, if x is less than 0, since absolute value makes something positive, and then x if x is greater than 0. This question is asking us where, if anywhere, it is not differentiable, which means we need to look at the derivative. We know this absolute value graph is continuous everywhere, and we could assume this kind of looks like it might be a sharp turn, but let's see if we can mathematically kind of verify to ourselves that that is the case. When I take the derivative of a piecewise function, I take the derivative of each individual piece. So the derivative of this piece, the derivative of negative x, is just negative 1. And I'm going to write x less than 0. I'm not going to put this or equal to sign in here until I actually confirm that these two values are the same when x is equal to 0. So then I'm going to look at this piece. The derivative of x is positive 1 when x is greater than 0. So now I'm noticing that these two pieces are not the same when x is equal to 0, which means the limit as x approaches 0 from the left of f prime of x, because we're talking about the derivative, is not equal to the limit as x approaches 0 from the right of f prime of x. Therefore, it is not differentiable when x equals 0. Now, if you feel up to trying number 2 on your own, I encourage you to do so. Let's try and create some room here. All right, the derivative here, f prime of x, would be 2x if x is less than 0. And again, I'm waiting on whether or not I can write that or equal to. And it's 1 if x is greater than 0. So what I need to look at here are the left and the right-sided limits. So if I look at the limit as x approaches 0 from the left of f prime of x, the derivative, if I plug 0 in there, I get 0. If I look at the same thing from the second piece, the limit as x approaches 0 from the right of the derivative, f prime of x, we get 1. These are not the same, therefore not differentiable when x equals 0. And last but not least, number 3, let's go ahead and find that derivative. F prime of x is going to be 2x if x is less than 0. And it's going to be 2x if x is greater than 0. And what I notice is immediately these are exactly the same, so I can add an or equal to this piece. And then I can show using limit that this is actually going to be differentiable everywhere. But let's show that the limit as x approaches 0 from the left of f prime of x is going to equal 0, which is also what we get if we just plug in 0. And that's equal to the limit as x approaches 0 from the right of f prime of x. Therefore, this is differentiable everywhere. So negative infinity to infinity. So just like with continuity, when you have a piecewise function, analyze the left and right-sided limits, the behavior for both pieces of the function, identify if the limit from the left is the same as the limit from the right, is the same as the value of the derivative at that particular point, in order for you to be able to talk about differentiability along the function. Let's move on and talk about the derivative of sine and cosine. We will prove this in class, but the derivative of sine is cosine, and the derivative of cosine is negative sine. And both of these facts you need to know, so you need to memorize those two facts. So let's use the fact that we now know the derivative of sine and cosine to find the derivative of a particular function. So we're going to find h prime of x. So the 2 with this term here is just a scalar. So I can just say that this is 2 times whatever the derivative of sine is. Well, the derivative of sine is cosine. So 2 cosine x. And we know that the derivative of 3x is just 3. So here is our derivative function. If, let's define a different function, let's say k of x is equal to 2 cosine of x, then when we take the derivative there, we would get negative 2 sine of x, because the derivative of cosine is negative sine. A huge application of a function and its derivative comes into place in physics, or any time that we're talking about position and velocity functions. So a position function is the location of an object at a particular time. Notation-wise, you're typically going to see this as s of t or x of t or y of t. And again, the variable being t because we're talking about its relationship to time. Something that calculus allows us to say is that velocity is really just the rate of change of position, which means that the velocity vector, or the velocity, is equal to the derivative of the position. So if I have a function for position, I can take the derivative of that to find the velocity function. Velocity has a sign element, meaning it can be positive or negative. And if it's positive, that means that it's either moving to the right or it's moving up. If it's negative, that means it's either moving to the left or moving down. And if it's 0, that means the particle, or whatever object we're talking about, isn't actually moving at all. A couple of other notation things. We would talk about the starting position, which would be at time equals 0, and that's often abbreviated or indicated using s sub 0, which reads s naught. Similarly, the starting velocity, which would be at t equals 0, would be v naught or v sub 0. Now, velocity has an element of sign, we just said, but speed does not. If you think about the speedometer in a car, there's no negative speed. When you are decreasing in speed, it's still showing the positive value. It's just getting smaller. So speed is the absolute value of velocity. So speed will always be positive, and you can remember that by thinking about looking at the speedometer in a car. Displacement is talking about the final position minus the original position. So it doesn't matter if I move 4 steps left and 2 steps right and 4 steps left and 2 steps right. All that matters is how far I have traveled how far I am from where I started. So if I am at my house and I drive to the grocery store and I come back home, my displacement is 0 because I ended up exactly where I started. As opposed to total distance, my car would tell me I have traveled about a mile to go round trip to the store. So total distance does take into account if we're changing direction, if we're going back the same way that we came, that would show up on the odometer in the car. I can't go backwards and take mileage off of my car. So let's apply this a little further. If we are given a position vector here, we could find the velocity vector simply by taking the derivative of each term. And we know that the derivative of t to the third, we drop the exponent down to get 3t, and then we decrease the exponent by 1 to get squared. The derivative of t is just 1. So here is our velocity vector given the position vector. Let's go ahead and look at an application of position and velocity. Let's go ahead and see how the relationship between position and velocity can help us analyze a problem in context. So here it says, use the position function given for an object moving in a horizontal line to answer questions 2 through 7. Question 2, what is the object's initial position? Well, the initial position is what we get when we plug 0 into the position function, which is 0 minus 0 plus 24, so is 24, and we don't want to forget our units, feet, and seconds. So the initial position is 24. It starts at spot 24 feet. Number 3, what is the velocity of the object at 1 second? Well, the first thing that we need to do is figure out what our velocity function is, which means we need to take the derivative of the position function. If I drop 3 down, 3 times 16 is 48, now t to the second power. 2 times 36 is 72, so minus 72t. And then I'm going to plug 1 into that to figure out the velocity at this value, which is going to be negative 24 feet per second because we are moving feet per second. Number 4 says, what is the speed? Meaning we're going to look at the absolute value of the velocity, in this case, at 1 second. Well, we just found that here. If we make it positive, which we are doing because we're taking the absolute value, we get 24 feet per second. Number 5 says, at what time or times is the object at rest? Remember, being at rest means that velocity is equal to 0. So we can take the velocity function that we found in number 3 and figure out when that's going to be equal to 0. So 0 equals 48t squared minus 72t. I'm going to factor here. I know that 48 and 72 are both divisible by 24, so 0 equals 24, and they both have a t in common. So 24t times 2t minus 3, that's going to give me t equals 0 and 3 over 2. Something to keep in mind, if one of these answers was negative, I would not include that because we're talking about time, and negative time doesn't make sense. So just remember the context of what we're talking about to make sure the answers that you're finding make sense. Number 6 says, over what time intervals, so we're looking for t values, over what time intervals is the object moving right or moving left? So I'm going to draw a little number line here to help me keep track of what's going on. We know that we're starting at time 0, and we know based on number 5 that at 3 over 2 seconds, the velocity is 0, and that's the only other time that the velocity is equal to 0. And I'm going to rewrite that velocity function down here just so that I can see it more easily. So what we need to know is what's happening here in between 0 and 3 over 2 before it stops moving. Is it moving left or right? Well, how do we do that? We think in our head, what happens if I plug in a number in between these two numbers? So something easy to plug in between 0 and 3 over 2 would be what happens at 1 second. And we actually already found this, right? We found this right here in number 3, that we get something negative. We get a negative value if we plug in any number between 0 and 3 over 2. And we just picked one number in between them that was easy to plug in to figure that out. The reason that it has to be the same over the entire interval is because in order for it to change direction, the velocity would have to be 0. And we already said the only places that the velocity is 0 is at 0 and 3 over 2. So now we want to know, okay, what's happening from 3 over 2 on? So we're going to think about what happens if I plug in something bigger than 3 over 2, like 2. Well, if I plug 2 in here, I would get 48 times 2 squared, or 48 times 4, minus 72 times 2. And I don't care what this number is. I just care if this number is positive or negative. And this is going to give me a positive number, so I'm going to put a positive here. Now, anywhere in this little sine chart that there is a positive value, that means that the object is moving to the right. So we can say it's moving right on the interval from 3 over 2 to infinity. Make sure you're using parentheses because at 3 over 2, it's not moving left or right. It's not moving at all. And then we can say that it's moving left on the interval from 0 to 3 over 2. Remember, we're not going down to negative infinity because this is talking about time. So both of these are in terms of seconds. And we can see this from our number line. We can tell where it's positive means it's moving right or up, but since we know we're talking about horizontal movement here to the right, and where it's moving left is where our velocity is negative. All right, last question in this part, number 7. What is the total distance traveled between 0 and 2 seconds? Total distance, remember, that's asking you to include anywhere that it stops. So we care about what's happening at 0, and we care about what's happening at 2, since we're looking at the interval from 0 to 2. But we also care about anywhere that the velocity is 0, which we found out in number 5, and again looked at in number 6, that it stops at 3 over 2 seconds. So we care about what's happening for each of those values. Well, if we plug in 0, we get 24. We did that on number 2. To find the position for 3 over 2, we need to plug 3 over 2 into this position function. And to save you time, I know that you could work this out on scratch paper. 3 over 2 to the third times 16 minus 36 times 3 over 2 plus 24. To save you time, I'm going to tell you that that gives you negative 3. And similarly, if we plug 2 in, I'm going to tell you if you plug 2 into this function, you get 8. So what we're asking ourselves is how far is it from from 24 to negative 3? Well, I'd have to go down 24 and then go down 3 more. So distance-wise, and distance is always positive, it's traveling 27 feet between when it starts and when it stops moving at 3 over 2. Then between 3 over 2 and 2, when it's changing direction, we're moving from -3 to 8. Well, -3 to 0 is 3, and then 8 more gives me 11. So to find the total distance, I'm just going to add those two numbers together to get 38 feet is the total distance that's traveled. Total distance. Now, to find the displacement, we just care about how far is it from where we started to where we ended. So we're just looking at s of 2 minus s of 0, and we already found those numbers. 8 minus 24, the total displacement is going to be -16 feet, which means by the end, we have moved 16 feet to the left. That's the displacement from start to end. All right, let's look through one more example. In this last example, we're going to look at a graph that relates position to time for a function of an RC car. And we're going to answer this question by looking at the behavior between each of these points, A, B, C, D, E, F. And we're going to tie that to the calculus talking about the rate of change or the derivative, which is really just the slope between potentially 2 points. So number 10 says, was the car going faster at point A or point B? And what that is really asking is, where is the slope steeper? So if I drew a tangent line here, and if I drew a tangent line here, which of them appears to have a steeper slope or a more straight up and down slope? And that looks to be B. The next question says, between which 2 points is the car stopped? Well, when is it stopped? If it is stopped, that means that we would be looking for a slope of 0 because it's not moving left or right. The position is not changing. And that appears to be happening between C and D since the slope is 0. The last question says, at what point is the car's velocity the greatest? Well, the velocity is going to be the greatest when we have the steepest positive slope. So if I look at what's happening at each of these points, I know at D, E, and F the slope is negative. So I'm looking at A, B, or C. And it looks like B has the steepest positive slope. Then it asks, at what point was the car's speed the greatest? And that just means the steepest slope regardless of positive or negative, since speed is always positive. So we're looking at B, and then we're going to compare that to the slope of these three. And it looks like to me that the slope is the steepest at point E. So again, tying that relationship between the rate of change or the slope of the position function to give us velocity. Let's recap what we learned in this video. We first reviewed finding derivatives and talking about differentiability, focusing on piecewise functions and looking at the left and right-sided limits of the derivative. We then talked about the derivative of sine and cosine and that relationship and looked at some examples there. We then defined or identified the relationship between position and velocity, that velocity is the rate of change of position, and how we can use that in context to help us answer all different kinds of questions. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.